let's now talk about clustering, which is another technique out of the field of unsupervised learning. So kind of, as you already know, clustering intuitively is an algorithm where I look at some data and I want to find kind of clouds of data which form clusters which are closer to each other, and where I could maybe deduce that those data points have something in common. This can be something very useful, for example, in situations like when you work with customers, for example, for Amazon, where, say, it's very complicated, say, to fit a model, a supervised learning model, and say, how likely is it that maybe I like a certain type of book? I could obviously try to build a model, but it would be very complex to kind of build a model where for each book I would have to fit a model and see whether what would be the kind of likelihood for me liking this type of book. Well, what might be what might be much more useful could be, for example, to say, let me just take all the properties, all my previous purchasing history, and maybe try to cluster all the customers and see whether I belong to a certain group of customers. So if I can do a clustering exercise, I could maybe figure out that I'm somehow similar to other type of, say, academics which buy similar books. And now if any one of those buys a certain type of book, the system can now go and recommend the same book to me. So there's a way where this recommendation system actually doesn't necessarily use supervised learning, but it could just use, say, clustering to group customers into different groups, and they say if one of them buys something, I will recommend it to everyone else in the cluster. That's one example where, for example, we could use clustering in practice. Now, the algorithms we talk about here are two. There's k-means clustering and hierarchical clustering. So in k-means, as a kind of name a bit suggests, I will look at a case where I will set the number of clusters. I will set it equal to k. So there could be 4 clusters, 5 clusters, but I have to define it in advance. Now, hierarchical clustering gives me a kind of hierarchy of clusters where I could have the possibility of just having a gigantic cluster of all the data, then 2 clusters, 3 clusters, up to, say, n clusters, where each data point is its own little cluster. And I can look at all this hierarchy and choose which level of clustering do I want. So k-means is for a fixed level of fixed number of clusters, and hierarchical basically gives me a hierarchy of any number of clusters. So those are the two algorithms we will be looking at, and the first one is k-means. So in k-means, I look at something which is called the within cluster variance. This is just a measure of kind of how good the cluster actually is. So this is the expression. Again, it looks a bit messy, but just remember that kind of it's just, what is it, 1 over ck, which is the number of points in this cluster, and then I have this double sum over m and n, which are 2 points in the cluster, and then I have basically this xmj xnj difference squared and then summed over j. So this thing here, I mean, this is just the distance basically between vector xm and vector xn distance squared. So effectively what I'm doing is I have a cluster here and I look at all pairs of points. So this could be point m and this would be point n. I calculate the distance and kind of square the distance and sum it all up for all the distances within this cluster here. So for all those distances, I will just sum them all up and see what is the total sum then. Obviously, if the cluster is very compact, the sum of all these distances will be smaller, whereas if there would be one point very far outside, then obviously there will be a lot of connections of these points to other points here, which will kind of increase the value for w here. So the idea is that the clustering algorithm will try to avoid something like this, because this will basically create a very large values of w's, and what the algorithm is actually trying to do is minimize the sum of all these w's. So I want to find the possible partitions such that the sum of all the within cluster variations is minimum, and this is the kind of objective of this algorithm. Now it already kind of cost us a little bit of work to write this down, but actually solving it is even more difficult, and this already it looks a little bit like the issue we had with the full subset selection, where once we had these combinatorial problems, it's actually quite tricky here as well. Kind of how many possible ways are there? If I have k clusters, there could be 5 clusters. How many ways are there to say partition 1,000 points into 5 different clusters? And again, we have those large numbers like 1,000 choose 5. Those are large combinatorial numbers, and we have to kind of work ourselves through all of those combinations, and for all of them sum up all the differences. So it's a very hard optimization problem. So this is something which is kind of nice as a definition, but in practice it's a very hard problem. The same as a subset selection. It's nice to say I will just look for the best 3 predictors, but then actually looking at all the combinations, it's very computationally intensive. So here again, there actually exists a kind of approximate algorithm which is very, very simple and which gives an answer which is quite close to this objective function. It's not the same, but it's quite close. And the algorithm looks actually quite a little bit different. And how it works is, let's just start with our points, and let's just start by randomly labeling them with k different labels. So I kind of randomly label them, and then I keep on iterating over the data, and for each of those random labels I calculate the centroid and then reassign the labels to the closest centroid basically, and I keep on iterating and iterating until the algorithm converges. So this is very abstract, so let's just look at a kind of little example. Let me try to draw something here. So say I have a number of data points. So here are some data points. I'm just drawing something which is a bit random, but which might have some clusterness to it. Imagine I had those data points. I'm looking for k means clustering for k equal to 4. So I have 4 different clusters, and we can just kind of color code them in different colors. And let's just say the first step is randomly assign labels. So I'm just kind of some points here are randomly chosen red, some other points are randomly chosen blue, some other points are randomly chosen red, and some other points green, sorry, and some other points are randomly chosen orange. So that could just be my starting point of my my clustering. So first step would be take all my points and randomly assign them to a cluster there. Now I have done this, and I can effectively calculate for each of these clusters the centroid. This would be the center of mass. So here we can have a look. Where, for example, is the center of mass for all the orange points? It's approximately here, basically. Now I can ask, where's the center of mass for the blue points? It's approximately here. Now where's the center of mass for the red points? It's approximately here. And where's the center of mass for the green points? Is probably also approximately here, quite close to this one. It's difficult to do that exactly. Maybe it's even a bit closer to the left because there are 3 points on the left. So roughly about there. Those would be the centroids, the center of mass of all the points in the given color there. So the 4 green points have a center of mass which is roughly here. The 4 yellow points where the yellow cross is, the 3 red ones roughly there, maybe it's even more or less there. And now what I do in the next step, I look and I reassign the colors to the closest centroid. So I would, for example, say, well, what are all those points? For example, all the 3 points here, they are closest to the green centroid. So this, this will actually become a green point. So they're all closest to the green dot here. And this one is also closest to the green dot. So this one becomes green as well. This one is also closest to the green dot. Whereas, well, the other ones is kind of debatable, but this one might be closest to the yellow dot. This is also closest to the yellow dot. This one here again might be closest to the green dot. It's rather close, so it's hard to see that. And now this point here is closest to the red dot here. This one as well, but say this point here I think is closer to the blue one. This one as well is closer to the blue one. This one, hard to say, but it's probably also, well, it's probably closer to the red dot, I would say, just by the eye. So it's all a bit tricky to see that with the eye. But now we come to a point where effectively, maybe the last one is hard to say. I would probably say this one is closer to the blue one. Again, they're very close, but let's just assume it's closest to the blue one. But now I have reassigned the labels and I can just redo the exercise. So now I get rid of my old centroids and say, let's just compute the new centroid. So the kind of center of mass of all the green points is here. The center of mass of all the yellow points is here. The center of mass of all the red points is here. And the center of mass of all the blue points is here, basically, roughly speaking. Now I can just redo the exercise, basically. And now I can actually say, if I redo the exercise, for example, now obviously those points are still closest to the yellow point, but now this guy is also closer to yellow than to green. This one I would say is also closer to yellow than to green. And now the other 3 dots are still closest to the green dot here. And now up here, I would say that now all those ones here are now, so all those ones here are now closest, I would say, to the blue dot actually. And now I've reassigned the labels. And now I would do basically get rid of the centroids again. And I would do yet another iteration here. So now I can see that the new yellow centroid is about here, basically. The new green centroid, it's about here, maybe. Red, there's only one red dot left. Sorry, this one here was a blue dot here, but so there's only one red dot left, which is here. And then the blue centroid is roughly here. And now I'm getting more or less to my last step of the iteration. Now all those points here are blue. This point here is red. Now all those ones are kind of, this one is hard to say, but so those are orange here, and those are effectively green. So those would be my clusters. It really depends on the exact differences, whether this last point here, this one here, whether it will eventually turn out green or orange is a kind of tough call here, but you will see how it ends out. So at some point the picture wouldn't change anymore. For example, up here things will remain the same. The blue dot will remain blue and the red dot will remain red. And unless this last point here decides to become yellow at some point, effectively this picture also doesn't change. So effectively I found now the 3 different clusters by just iterating. And you saw it took me like, it was a bit tedious, it took like 3 iterations or so, but this algorithm actually converges quite quickly, like 3 or 4 iterations and it is done, basically. It goes very quickly and it finds me those clusters. So here's one cluster, here's a blue cluster, here's the red cluster, here I have the orange cluster of points, and then I also have the green cluster of points. So it found the clusters and they all look like reasonable clusters. So this is exactly how k-means clustering works, and it's an approximate algorithm, but you can actually show, and I do not want to do the exact math, but there's a little, it's not a derivation, but there's a little explanation in the Introduction to Statistical Learning textbook, how actually this iteration, each step of this iteration here effectively reduces the within cluster variation. So while we're not really guaranteeing the minimum, we can at least guarantee that each step of this iteration necessarily minimizes or not, it necessarily decreases the within cluster variation. So as I keep on going, I make it smaller and smaller and smaller. I'm not showing, and you can't actually show that you will actually find this minimum, but at least it will make it smaller and it converges to something. It should also be said that, you know, the color coding isn't fixed, because the colors, kind of the initial labeling is random, and it could have been that obviously now this is the red cluster, this is the blue cluster. It could have been that I would have gotten the same clustering out, but potentially with different color code. It could have been that the one on the bottom right would have been blue there. So I can kind of get different clusterings with different colors. I could even get kind of slightly different clustering out of there. This is why it's not really an exact minimization. It doesn't really do this minimization here, which would have an exact solution, but it's some approximate algorithm which does give a solution rather quickly, and something which is quite close to the actual solution we will get from here. But it's just an approximate algorithm. So far for k-means clustering, and here we can have a look at an example. This is the same data as we looked at before, this NCI 60 data, and we know it's high dimensional, and so the only way to look at it really in 2D is by looking at by plotting it in the kind of space, the two-dimensional space of the 2 principal components, exactly as we did when we talked about principal component analysis. And I can see that my clustering actually finds clusters which are quite nice. So they look like clusters also in this projection, which tells us that the clusters are good, but also the projection is good, because we can actually see those clusters by eye. So here's kind of the blue cluster here, and I have the green cluster, and I now actually, and so on, the other clusters as well. So there are 4 clusters in total here, and I actually put some labels on the points. So again, this is all unsupervised learning, so I do not have any labels on the data, but actually this data set NCI 60 actually does have some labels. It's just we didn't use those labels. We just did the unsupervised learning analysis, PCA and clustering, but we didn't use any of the labels. But actually we can see, if we get out those labels, that actually some of these cancer types which are within each cluster are of similar type. So actually the clusters have a meaning here. We can see most of those clusters of the kind of cancer cells in those clusters here at the bottom, the blue one, are melanoma. So we can, and up there is leukemia. So we can see similar type of cancers within similar clusters. So they actually have a meaning. For example, if I didn't have the labels, I could have maybe concluded that whatever cancers are are effectively here in say, whatever, the blue region here, that those cancers are maybe of a similar type, and maybe I could have figured out for a few of them the point, like I could have tested maybe 2 of them are melanoma, and maybe would have concluded that probably all of them in this cluster are melanoma. So I can actually learn something from those clusters, and it's very reassuring that actually, given that I do know the labels, that my clustering actually kind of gives kind of results which are reasonably consistent with the existing labelings, which obviously I didn't use to perform this clustering. This clustering just uses a kind of distance information between the points. It's just, look, I see all these points, so how can I have clusters in with regard to different points being kind of closer to each other than others? So this is just an example for k-means clustering for k equal to 4, and now I can also look at the other technique I wanted to discuss, which is hierarchical clustering. So in hierarchical clustering, I want to kind of build up a hierarchy of clusters in a way where, and this is again a kind of greedy algorithm where again we avoid this combinatorial issues we had, say, if you wanted to solve the exact minimization problem, which I presented earlier when talking about k-means, and do it in a greedy fashion where we say we start with each observation being its own cluster. So this will be our starting point, and then we kind of say, well, now we just join clusters, we merge clusters, and we merge 2 clusters which are the closest. So we have n data points, each one is its own cluster, and now we look which 2 of them are closest and we merge them. Now we have n-1 clusters basically, and we continue to merge them. The only kind of subtlety here is how I define those distances there, especially if it's 2 points. It's simple. I have 2 points, Euclidean distance would be a valid distance measure. But if I have multiple points, for example, I had so this would be kind of my one cluster here, and this would be another cluster, and then I have this cluster here and this cluster. I have kind of 4 clusters, and now I want to join them to 3 clusters. So I want to find the 2 clusters which are closest and merge them. But then obviously the question is, how do I define the distances here? Could I, for example, define what's the distance between say this cluster and this cluster here? It could be, for example, I could define it as the distance between this point, between this point here and say the centroid of this cluster, which could be one definition. Or I could say I define the distance between clusters as the shortest distance between any points in each of the cluster. Or there are different ways, but depending on how I define it, for example, if I define shortest distance, then maybe those 2 points would be the closest, and I would join this thing here as a new cluster. Whereas if I maybe defined it as the distance between centroids, then potentially this distance here might be larger than this distance, and in which case I would have joined those 2 data points. So kind of which ones I join define a little bit on a distance measure. So I have to come up with a definition of distance measure here, which could be like shortest distance between clusters, or the distance between clusters could be defined as the distance between the centroids, or average distance or something like this, or maximum distance, minimum distance between any points. There are different definitions, and depending on which definition I use, I can get slightly different clusterings. But the basic idea is start with every point being its own cluster, look for the 2 closest clusters, join them. Now I have n-1 clusters. Look for the 2 closest clusters, join them. Now I have n-2. And I keep on going until I have only 1 cluster left. Everyone is in the same cluster. And this will give me a full hierarchy. And we can look at a nice picture here. So this is what is called a dendrogram, which is this kind of hierarchical tree structure of the clustering here. So at the beginning, effectively, on the top, I have basically everyone being in one cluster here. At the bottom, I have basically everyone being its own cluster here. So this is every data point this in its own cluster. So if I look at the top, I have just one cluster. If I look at the bottom, I have like everyone its own cluster. But I could have kind of intersected here. Now I would have just had two clusters. So this cluster here would have incorporated all those points here, and this cluster would have incorporated all those points here. Now I would have had two clusters basically, but I could have also decided to intersect at different points, say here, and I would have maybe had 5 clusters here. And I can really kind of vary this, and this hierarchy of clusters basically gives me a way of determining where I would really like to choose the clustering. And here I can see example. For example, here I choose this threshold, and I will get a given number of clusters. And if I say, if I wanted a given number of clusters, I can just look where do I have to cut to say get 5 clusters or 4 clusters, and so on. I will always find a point where, for example, if I wanted 2 clusters, I will cut here. If I wanted 3 clusters, then I would try to cut, well, it's a bit, I would try to cut here. Now I had 3 clusters, and if I wanted 4, I would go slightly below, but I could decide how many clusters I want, and then I can cut there. And I could now look at the example. So for example, say I take the dendrogram and I choose the cutoff so that I have 6 clusters, and this is roughly what I would get. So it looks kind of similar to the other one. Obviously before I had 4 clusters, now I have 6 clusters. Some points look a bit off, like there seem to be some wet dot in here, but obviously I mean, distances here, I mean, this, you might ask, why is this point in this cluster in the violet one, if it seems to be, why is the wet dot there? It seems to be so close to the other color, but that's obviously misleading because I'm just looking at a 2-dimensional projection, whereas in reality the space is very high dimensional. So this point here can be very far away from this other point here, because maybe they're very far stretched away in this other dimension, which I can't see because I'm looking right at it. So there's nothing wrong with those points being kind of a little bit mixed here, but it seems like this clustering is kind of a little bit more at odds with the projection I'm using here. But still, I get valid clusters, and they seem to be also roughly in line and consistent with the labels which weren't used for the clustering here. So yes, that's basically all for the hierarchical clustering and k-means clustering, which are the 2 ways of clustering which I wanted to discuss, which I think are also probably the 2 most commonly used approaches to clustering in unsupervised learning and in machine learning in general.